Hey again, I'm Thyme. Welcome to part 2. If you missed part 1, link is in the description down below. Last time we talked about measurements. This time, we'll be talking about the measuring. I'm sure you've measured a lot of things in your life before. Some you can just eyeball, others you've had to use instruments like using a ruler to measure your height, or maybe even a $1 million microscope to measure the diameter of airborne particles. There are so many kinds of instruments out there, each with their own intended purpose, that you're probably better off Googling them yourself. Regardless of how good or expensive your instrument is, however, measuring something will always have a degree of error. An error is the difference between a measurement and the actual value. Errors happen all the time and it's inevitable. Say you want to weigh my robot here with a scale. I know I said 5 kilograms in the last video, but I just estimated that based on how heavy he feels on my shoulder. If I want a more precise reading, I'd use a digital scale, so let's do that. Okay, here I have a scale that measures in 0.01 kilogram increments. This is called the instrument's resolution, which means that it can't effectively measure anything smaller than 0.01 kilograms. Now, let's put ribbit on the scale. The scale says 4.75 kilograms. It might seem like an exact number, but in reality, it could be 4.748 or 4.751, and we'd have no idea because the scale is limited to 2 decimal places. It could even be 4.741 because there's a chance that the scale doesn't round downwards. So, what do? You write it not as an exact number, but as a range of possible numbers. The left number is your range's median value, usually your average as well, and the right value is your uncertainty, or the distance between the median and the upper and lower limits of your range. This means that you're not sure if the actual value is exactly 4.75 kilograms, but you're sure it lies somewhere between 4.74 and 4.76. Simple, right? Now, best practice says that you should measure multiple times to be absolutely sure. So, let's say that you did. You redo the weighing, and you get different readings this time. Believe it or not, this happens a lot too. First, 4.74, then 4.74 again, then 4.73. Your new median is now 4.74, and your new range is now between 4.72 and 4.76. So your measurement is now something like this. Okay, we're done, right? If you're satisfied, sure. Of course, you can also continue repeating this process to try and get an even more accurate reading, but that sounds a bit tedious, and it brings another point. How much do you trust this scale in particular being correct? Let's say you're paranoid, and you really want to be sure. You weigh ribbit with a different digital scale, and you get the following readings: 4.81, 4.87, 4.83, and 4.85. From that, this is our new measurement, and here's our old measurement for comparison. This means a few things, but before we go there, I'll spoil it for you right now. Ribbit actually weighs 4.79 kilograms, and that's coming from his design datasheet, so we'll consider that his actual value. Now, if you had to guess, which one of these scales is more accurate, and which one is more precise? What's the difference? Accuracy is how close measurements are to an intended value. This is what people usually mean when they mention error, while precision is how close measurements are to each other. A common analogy would be shooting bullets at a target. A perfectly accurate and precise gun would always shoot close towards the intended spot, the center. If the gun is accurate but imprecise, it shoots generally in the center, but the bullets are farther apart. If it's precise but inaccurate, the bullets are close together but are noticeably far away from the center. Accuracy is usually quantified by relative error. That's measured value minus expected value divided by expected value. In this case, we'll put the average mass you measured in the measured value and Ribbit's actual mass in the expected value. You'll notice that whatever units these numbers have, you can always cross out and the result is unitless, aka a percentage. The lower the percentage, the lower the relative error, which means the higher the accuracy. In this case, both scales actually have the same magnitude of accuracy because they both have an error of 0.05 kilograms or roughly 1%. One is just negative or below the actual value, and one is positive or above. Meanwhile, precision is usually quantified by relative uncertainty. That's uncertainty over measured value. We'll put in our uncertainty value and the measured, or in this case, average value. The lower the resulting percentage, the lower the relative uncertainty, and the higher the precision. Between both scales, the first one is more precise because it has a narrower range, hence more consistency. In conclusion, accuracy tells you how far your measurements are from the target or ideal value, and precision tells you how consistent your measurements are, irrespective of whether or not they're correct. Manufacturers are usually kind enough to provide accuracy data for their instruments, so be sure to look out for that. Otherwise, whenever you feel like something isn't accurate enough or it's starting to lose accuracy, you might need to do some calibration. Calibrating your instrument essentially means adjusting or readjusting it to provide results within an acceptable range, typically using another instrument of proven standard or accuracy as reference. These kinds of instruments are usually reserved solely as reference material to standardize other instruments as opposed to directly being used for measurements themselves. It's always good practice to routinely calibrate your measuring tools, in addition to calibrating it from the get-go. You can do this with another instrument of yours that you assign as reference, or you can get licensed institutions to calibrate them for you, like the NIST in the US. Either way, you'd want to do this because, like people, instruments aren't perfect and they age over time. They can lose accuracy, something called a drift, and usually calibrating could fix that issue. They may also lose their precision, and that's a more difficult problem to fix. So try to take care of them and don't smack them around needlessly. By the way, drifting is mainly caused by the instrument, and errors like this fall into something called a systematic error. There are two other types of errors, and systematic error itself is divided into three. Instrumental errors are caused by an instrument's shortcoming, defect, or other effects under load. Environmental errors are caused by the environment, like changes in air pressure, temperature, humidity, and so on. Observational errors are caused by reading the instrument inaccurately or imprecisely, like how looking at a needle from different angles can give you different readings. Now up we go to the big types, where systematic errors are caused by the instrument. Gross errors are mainly caused by the observer, specifically due to negligence, bad judgment, miscommunication, and just all-around blunders. This includes mistakes like, whether intentionally or unintentionally, incorrectly setting up the instrument, misplacing decimal points, writing down the wrong measurements, and a bunch of other unfortunate lapses in judgment. The third and last type is called random errors. This encompasses errors that don't fall into the other two. Errors caused by unknown sources and happen through unknown means. They are unpredictable, can't be replicated, and usually beyond our control, like electrical noise, statistical distribution, and possibly fate itself. Now, this may seem like an environmental error because they're technically caused by the environment, But the difference is environmental errors can usually be replicated to give similar deviations from the actual value. Random errors are more sporadic. Environmental errors and systematic errors in general typically make measurements inaccurate, whereas random errors make them imprecise. So, although they're out of your control, you can effectively lessen random errors simply by repetition. Anyway, these categories can be a bit vague in certain areas, so don't be too fixated about it. What you should be conscious about though is the fact that you could be experiencing these errors without realizing, and that no measurement is perfect, but that's okay. All that matters is that you are aware of what errors you're susceptible to, and whenever it counts, you try to identify and quantify them. Now that's a life lesson for you. Okay, before we close this topic, I'd like to touch a bit on significant figures, considering we're talking about errors and all. We've been measuring with easy numbers like my height and Ribbit's mass, as in there aren't really a lot of digits involved. In reality, a lot of applications, even outside science and engineering, use more accurate measurements, and that can mean having a lot of digits. Significant figures help in indicating how many and which digits are necessary for you to keep in your calculations. So back to my height and Ribbit's mass, because I sure as hell won't be telling anyone my mass. These two quantities have 3 digits each, and all 3 are significant figures. What's a significant figure? Significant figures are digits of a number that are absolutely required to indicate the quantity of something. That means that you cannot remove or change any of these digits without changing the quantity. It'll get clearer as we go along, I promise. We start with the first 2 rules. 1. All non-zero digits are significant. 2. All zeros between non-zero or significant digits, called trapped zeros, are also significant. In a volume measurement of 1,505 liters, there are 4 significant figures. Changing any of those digits would mean a different volume. Now, it's been fairly obvious so far, so what's the point? Well, here's where it gets interesting. 3. Zeros to the left of the first non-zero digit, called leading zeros, are not significant. I can write my height as 0176 or 00176. It doesn't change the measurement, so doing that is useless. If it's a decimal and not an integer, it's still not significant. I can write my height alternatively as 0.00176 kilometers or 0.0176 hectometers. They're redundant because they're just other ways of saying 176 centimeters with more zeros, and there would still be 3 significant figures. This means leading zeros are always removable and addable as long as you follow along with the unit. But no matter what unit you use, the numbers 1, 7, 6 in that order always need to be present. 4. Zeros to the right of the first non-zero digit, called trailing zeros, in a decimal are significant. Ribbit's mass of 4.79 kilograms is the same as 04.79 kilograms, but not the same as 4.790 or 4.7900 kilograms. This is because when I say 4.79 kilograms, it could be the result of a rounded 4.786 or 4.792 and not necessarily 4.790 or 4.7900. You are only allowed to do that if you are absolutely sure the digit following the 9 is a 0, in which case you'd be adding one significant number. Remember though, only in decimals. 5. Trailing zeros in an integer may or may not be significant. In the measurement 8,100 grams, there could be 2, 3, or 4 significant figures. This is because we don't know if the writer means it's exactly 8,100 or roughly 8,100 grams. As in, it's rounded from say 8,130 or 8,099. Rounding is perfectly okay. It's just that in this case, you can't write a rounded number without it looking like an exact number. This only happens in integers though. The moment you write it as 8,100.0 grams or 8,100.000 grams, it's now a decimal, and all the digits are significant as per rule number 4. This is because it's unreasonable to think that anyone would round, say, 8,101 or 8,099 to 8,100.0 instead of just 8,100 without the decimal point. 6. An exact number has infinite significant figures. A lot of quantities are measured in exact numbers, like the number of eggs in a pack. You count eggs in whole numbers, so that's 12 eggs for instance, which you can write as 12.0000000 all the way to infinity, with all the zeros being significant digits. Because you know for sure there's no such thing as a 12.001 egg, only exactly 12 or exactly 13. That's pretty much it. Aside from these rules, it's important to note that the number of significant digits rely heavily on your measurement resolution. If the resolution of your scale is 2 decimal points, you can't claim to have measured a mass of 5.100 kilograms, because the instrument doesn't have that kind of precision. Anyway, it's also important to note that sometimes you're going to have to use long numbers in your calculations, such as incredibly accurate measurements or math constants. It would be a huge bother to have to include all those digits throughout your calculation, especially for constants like pi, where there's literally an infinite number of digits, and it can waste your time or waste computer resources. So, what do? You don't use them all, obviously, only the most important digits. The more left the position of a digit, the more significant it is, meaning the more change it brings to your calculations. People typically write pi as 3.14, which is in 3 significant figures. It's not that the rest of the digits aren't significant, they're just not significant enough for the user. You can choose to write in 4 or 5 significant figures to get a more precise result. This applies to all other physical quantities as well. So when you measure something with more digits than you think is necessary, you can choose to leave out the less significant digits and round them up or down to fewer significant figures. Just be aware that this also means introducing a bit of error to your final result. Now you've probably noticed that most of the ambiguity comes from zeros. To avoid using a lot of zeros in your quantity, be sure to use prefixes. Instead of writing 1,500 grams with 2 ambiguous zeros, you can write 1.5 kilogram and not have zeros at all. Or, better yet, you can write using what's called a scientific notation, which looks something like this. That way, you get to keep your unit and leave out the zeros. You can also indicate how many of those ambiguous zeros are actually significant by just adding it behind the decimal point. This kind of notation is used a lot in scientific calculations to simplify numbers that are too big or too small. The standard form would be m times 10 to the power of n, where n is chosen so that m is between 1 and 10. What it means is that in scientific notation, you cannot write 1,500 grams as 0.15 times 10 to the power of 4 grams or 15 times 10 to the power of 2 grams. M needs to be 1.5 or 1.50 or 1.500 depending on how many of those zeros you determine to be significant. Again, this is for simplicity's sake. You can also use this opportunity to round your measurement to however many significant figures you want. The 10 to the power of n does not count towards the significant figures. If you want to be perfectly scientific, you'd want to write measurements in scientific notation and SI units. This may seem a bit convoluted for now, but it massively makes calculations clearer in a lot of cases later on. But that strikes another point. How do you perform calculations on numbers with different significant figures? Well, if you multiply or divide two or more numbers, the result needs to have as many significant figures as the least number of significant figures among the calculated numbers. 5 6 times 3 6 divided by 10 6 equals 3 6, because 3 is the least number of significant figures. If you add or subtract, the result's rightmost significant figure position needs to be the same as the leftmost significant figure position among the last significant figures of all the calculated numbers. Example: between these decimals, the last significant figure with the leftmost or highest position is 0.1, so 1 decimal point. Hence, the result needs to have 1 decimal point. Got it? Feel free to pause the video to take it all in. We'll skip transcendental functions like derivatives and logs for now. Just remember to round to the required significant figure after you get the result, and not before. Also, be aware if any of your numbers is an exact number, because you'll have to treat it as though it has infinite significant figures. Why so convoluted, Thyme? Well, it has to do with propagation of uncertainty and error. Since each measurement you use tends to have a degree of error and uncertainty, as you operate on them, the error compounds, and you'd want to be conservative with your estimates. Ultimately, no matter how accurate your measurement is, if you operate it with another way less accurate measurement, your end result will depend on the least accurate number. If you're not that particular about the error, or if you just want a quick or rough calculation for your physics class, like a lot of people, feel free to disregard these rules. But if you're designing a rocket and you're responsible for the lives of 5 astronauts, then you might want to put in the little extra effort. But hey, considering you've watched this video up till the end, you've put in some extra effort in yourself. Congrats! I hope you've learned the error of your ways, and I'll see you in the next video. Thank you so much for watching. Hopefully it's been helpful. Please like the video if you like it, dislike the video if you don't. Feel free to share or leave a comment if you'd like to add anything or if I got anything wrong. Do subscribe if you want to see more content like this. Have a nice day and see you next time.